Hi everyone, in this video, I will demonstrate how to use DSRA PMLO. Before we start, let's look at how DSRA PMLO works. The first is the recorded signal that we want to sample more efficiently. This is one input. The other input is a user-defined reconstruction error threshold, which guides the optimization process. DSRA PMLO then performs adaptive sampling to select only the most informative data points. Using these sampled points, it reconstructed the original signal and evaluates the reconstruction accuracy. Finally, the software reports the reconstruction error and the achieved sampling reduction, allowing users to balance accuracy and data efficiency. Now I will demonstrate DSRA PMLO using Visual Studio Code for both automated and manual modes. First, we create a folder to store the program. Let's call it test, and then we have open terminal. We direct to the folder, and then we copy git clone command. Once it's cloned, we direct to the program. And then we run the next command. This is for macOS. And if you use Windows, use this command instead. Same command for macOS, command for Windows. Now use this command to prepare the environment. Run one more command, copy paste. Once the installation is complete, the project is ready to use. Open Visual Studio Code. Now we find the program, DSRA PMLO, and open. Open a new terminal. This is the main file you need to interact with. This file controls the complete workflow of the software. The configuration section looks like this. We can configure the input data file, whether to use automated or manual mode, the target column, the target data size, the error threshold. If you use manual mode instead, you will also need to select the range for parameter E and S. The file parameter specifies the input dataset. The target column parameter specifies which signal column will be reconstructed. In this example, the target column is amplitude. All the data files are in folder data. Now let's run the automated mode. The mode is set to automated. Automated mode performs the complete optimization automatically. It begins with a coarse grid search over the ENS parameter space, identifies promising regions, then performs a refined search, and finally applies dual simulated annealing to obtain the optimal parameters. Now let's run the automated mode. Simply click Run, or we can copy the command and run in the terminal. The software loads the data, splits into training and testing datasets, performs the optimization, reconstructs the signal, and evaluates the optimized parameters on the test set. In the result, the plot shows the number of samples, error threshold, and sampling reduced. For the detailed result, it's printed in the terminal. Now let's look at the manual mode. Change the configuration to manual. Manual mode is designed for users who would like more control over the optimization process. Instead of searching the entire parameter space automatically, the user progressively narrows the search region based on the visualized grid search results. It includes 3 steps. Step 1, coarse grid search. Step 2, zoomed grid search. And step 3, fine grid search. Let's look at the parameters we need to work with. There is parameter E and parameter S. The first value represents the start of E. The second value represents the end of E. The last value represents the step of E. Similarly, for S, start, end, step. Now let's work with the program. We set mode to manual. And for the first step, we can adjust the range for E into wider range. Let's say 40. We want to change the range for S to start at 0. Now let's save the file and run. This shows the total length of data, which is 400. This shows the length of training data. which is 240. The software first performs a broad grid search and generates a heat map of the E and S search space. On this figure, the horizontal axis represents E, the vertical axis represents S, and the color indicates the number of selected samples for parameter combinations. The objective is to locate regions that achieve the required reconstruction accuracy while selecting fewer samples. That means we want this area that is selected as low as possible. We want number of measurements to be low. So we can see that at range 2 to 6, number of measurements are low. We can see they are dark purple. And the values for E would be from 2 to 6. We can make it a bit wider so it can be more accurate, where let's say from 1 to 7. And then we look at S, similarly between 0 to, let's say, 10. To cover wider range, we make it 0 to 20. So 1 to 7, 0 to 20. Then we're passing 1, 7, step 1, 0, 20, step 1. And similarly, after inspecting the figure, for E at range 3 to 4, the value looks good. So we can make it a bit wider just to cover more range. Then that will be 2 to 5. Similarly, for S, we can see when it's at 0 to 2, the result looks good. So we can just pass in 0 to 2. So 2, 5, 1 step, 0, 2, 1 step. The last step, step 3, fine grid search. Finally, the selected search region is passed to the dual simulated annealing, which computes the final optimized parameters. The optimized parameters are then evaluated on the test dataset, and the final reconstruction plot is displayed. This demonstration used Visual Studio Code, which is a recommended environment for running DSRA PMLO, especially when using the interactive manual workflow. If you prefer not to install Python locally, the GitHub repository also includes instructions for running the software in Google Colab. Simply follow the setup steps provided in the README file. For installation instructions, project documentation, and additional examples, please refer to the GitHub repository. Thank you for watching.